Hello, this video is going to examine two-sample hypothesis testing for a difference in proportions. And we do this using the z-test for P1 and P2, proportions for two respective samples. They must be randomly selected, they must be independent and large enough to use a normal sampling distribution. And by that we mean that the product of the sample times the proportion is greater than or equal to 5, as is the complement. The product of the sample with the complement of the proportion, which is Q, also has to be greater than or equal to 5. And that's true of both samples, sample 1 and sample 2. The sampling distribution for the difference of proportions between two samples is normal, and the mean is the mean of differences between proportions. With standard error, shown down here, P bar times Q bar times the product of 1 over n plus 1 over n2, where the complement Q bar equals 1 minus P bar. And a weighted estimate can be found using P bar as equal to x1 plus x2 divided by n1 plus n2. And x1 is going to be the product of n1 times proportion 1, x2, n2 times proportion 2. So the different samples sizes by the proportions for those samples gives us our x values. And so the test statistic is going to be the difference of our population proportions. And the standardized test statistic for z is shown in this equation, which is our sample difference of proportions minus our population difference of proportions, divided by the square root of the product of P and Q for our sample times the addition of 1 over n1 plus 1 over n2. And that's where P bar, again, equals what we said before, x1 plus x2 over n1 plus n2. And then we'll continue on to our steps. So we begin, as usual, with our stated claim mathematically with HO and HA identified, with a level of significance alpha also determined. Give us our critical values. Here we use this equation to find our critical values. And then we determine our rejection regions using our z-score table. And we find the weighted estimates for P1 and P2. We then find our standardized test statistic using the before reviewed equation. We then make our decision to reject or fail to reject, and then interpret the decision in the context of the original claim. Here's an example. We have a recent survey that stated male college students smoke less than female college students. And that's something we're going to test. So for the males, there's 1,245 of them, but 361 claim to smoke at least 1 pack a day. And the females, we have 1,065, but 341 claim they smoke at least a pack a day. So at an alpha 0.01 level, can we support the claim that the proportion of male students who smoke at least a pack of cigarettes a day is lower than the proportion of female college students who smoke a pack a day? So there's our null. P1 is greater than or equal to P2, and then our claim. The claim is that males are less than females, so 1 is male, 2 is female. Our z-score here at the 0.01 level is going to be minus 2.33. And our P bar is going to be calculated using the x1 and x2 values, which are again substituted in the n1 P1 plus n2 P2 over n1 plus n2. That gives us 0.304. And our Q bar is just going to be the complement of P bar, so 1 minus that gives us 0.696. So because the product of 1245 times 304, the product of 1245 times 696, the product of 1065 times 0.304, and the product of 1065 times 0.696 are all over 5, we do satisfy our assumption for the z-test. So we move on here to find our test statistic using our equation. And here is that. Difference of proportions for the sample minus difference of proportion for the population. Again, we're assuming there is no difference there for our null. So that's just 0. And then down here in our denominator, our product of p bar and q bar times the addition of 1 over n1 plus 1 over n2. When we do that math, we get minus 1.56. We're not in the rejection zone, so we fail to reject the null. So there's not enough evidence at the 1% level to support the claim that the proportion of male students who smoke is lower than that of female students.